Welcome back, Precalc. Today's stuff, super duper tricky. Not really, but it's super tricky. And all that we're going to see is a little extension of what we've already written, and it's stuff that you've covered. So as always, super duper important. If I'm going too fast, how am I going to know it? You'll tell me. Cool. All right. So in today's section, which we should probably look and see how long this chapter is, because we're starting 4.3 today, and we get what is known, or we're going to focus on, right angle trig. Now, the word right angle is going to show up a ton, and I hate it. But if you don't want to have to write the word right angle, a truly accepted version of this is this shorthand, but I don't like it. You can use it. That's fine. I won't. I don't know why I don't like it. Cool. So, right off the bat, we're just going to make a couple comments. Today, we are in quadrant 1. We have, and we're going to use a little fancy math writing, an angle theta that exists in, that's what that symbol means. And let's think about quadrant 1. Where, angle-wise, would you be in quadrant 1? Between which two angles? 0 to 90 degrees. That's all fine and dandy, but I don't want it there. Instead, you'll give me 0 to some other number of radians. Pi halves. So all that we're saying with this statement is, check it out. We have theta between 0 and pi halves, which is just a fancy or really specific way to say we're working in quadrant 1. Now, the nice thing about this is if we draw any triangle in quadrant 1, it's always going to be a right triangle, no matter which quadrant we draw it in, as long as we follow bow ties and butterflies. And 2, it's an acute angle, everything's positive. This gets super easy to deal with. So, right off the bat, I'm going to sketch just quadrant 1. And it's going to not be perfect, but that's all right. So just quadrant 1, I'm not going to label everything, but that's quadrant 1 of my unit circle. Cool. Now, for any arbitrary triangle that I choose, and I'll switch color just to show it, let's say I want this to be my theta. We know that if I make this a right triangle, and I'll let you guys catch up because it takes a little bit of time to make a nice arc and such. Any right triangle that I ever draw, the hypotenuse is represented by something special on the circle. And what do we call it? The radius. So just for convenience, we'll make sure we call that r. We'll look at this distance and say, hey, that's just some distance in the x direction that we have to move. And then this other side, we'll just say that's some distance in the y. This is essentially the picture that we used when we defined the 6 trig functions the other day. Sine is y over r, cosine is x over r, so forth and so on. Now, from here, we get an idea that I guarantee everybody in here has seen this year if you're in my physics class, and we probably even talked about it yesterday. From this angle, instead of calling this y, we maybe know that we can call it a trig function, but I'm fine with holding off on that. From angle theta, this side is the opposite, the adjacent, or the hypotenuse. Opposite. So I'm just going to put here that this is OPP. Yeah, you know me. Hey, somebody else had it. Okay, this x side is what? The adjacent. I use ADJ. It's not an adjective, it's the adjacent. And this r up here is also something. The longest side of a right triangle, I saw you mouth it. The hypotenuse, which I'm going to just represent with height. All right. Think of me as your hype man. Nothing crazy about this. You've seen it. Now, even further, I don't think we have to go crazy into detail with this. Rather than defining these things as x over r and things like that, we have a nice idea that we have talked about, and I guarantee, I guess I can't guarantee, but everybody should know this and how to spell it. I don't remember how in detail I went with the Lakota chief, Anybody remember the name of the Lakota chief that I talked about earlier this year in physics? SOHCAHTOA. Gosh, how do you spell it? SOHCAHTOA. What is SOHCAHTOA and what do we use it for? It's our way to have a good way to remember how to find the sine of an angle, the cosine of an angle, and the tangent of an angle on any right triangle that you ever give me. Whether it's on a circle or not doesn't really matter. We have it. So what we're going to do is, this is all just kind of preface stuff. Our first true section today, I'm going to call this a new definition. A new definition, which we haven't used this very often. This is my shorthand, or my contraction, if you will, for definition. Defin, where I just let the apostrophe be the ish part of it. A new definition of our trig functions. Now, it is a really small change from what we did before. Sine, before we just said it was y over r, which that's fine and dandy. That's a good way to think about it. These are a little bit more formalized, and we're just going to jump in, and I'm going to always do the exact same order. Based on what you already know from SOHCAHTOA, I'm just going to give us a little, hypothesis is what it would be, but it's our given information. So, given an angle theta, we have a few nice definitions. Based on what you know about sine, cosine, and tangent, or SOHCAHTOA, we could define sine as y over r, which is what we did the other day. With regard to the triangle and the sides that we discussed, though, and SOHCAHTOA, how do we define the sine? Opposite and hypotenuse, and what happens between them? They divide, because these are all just ratios. Opposite over hypotenuse. Okay. Again, I want to stress, I'm always going to do this same order. Cos theta and tan theta. And then beside these, I'll do their respective matching parts, which is kind of annoying with the secants, but we'll deal with it. SOHCAHTOA. What's the cosine of an angle? AH is what I know. What do those represent? You're killing it. Adjacent over the hypotenuse. And the tangent? And I'll move this down just a skosh. What's a tangent according to SOHCAHTOA? Opposite over adjacent. Perfect. Okay. There is nothing, I hope, new about this, and I'm just going to check real quick, because not everybody has my physics class. You can keep it close, that's fine. Thumbs up says, yep, I knew this before we wrote this down just now. Thumbs down says, I don't really remember this. Somewhere in between, I don't care where you are. Just curious. Okay. What I want you guys to do is give me the other three. I'm going to write what next to sine? Always. Cosecant. And it's a weird switch that happens. I want you guys, I'll give you a second. Give me the cosecant of theta, the secant of theta, and the cotangent of theta. And I'm going to pause it and write it. This, I hope you guys are done in like 15 seconds. JV, if sine is opposite over hypotenuse, what's the cosecant? The hypotenuse over the opposite. Perfect. Hype over op. Okay, if cosine is adjacent over hypotenuse, Mickey, what is secant of it? Hypotenuse over the adjacent leg. And Charles, if tangent is opposite over adjacent, what do you reckon cotangent ought to be? Perfect. The adjacent side length over the opposite side length. Okay, we have these given. The most important thing with this, and when you saw trig as a geometer or as an algebraist, you might have gone from different angles. We could easily assign a different angle up here, and we would get stuff moved around. But we'll talk about the significance of that in a second. So, quick check using a unit circle, your brain, or anywhere in between, not just copying, I want you to do a quick example where I'm going to ask that you evaluate a few values for me. So, on our first one, I want you to, on A, we'll say theta is 2 pi thirds. I want you to find me the sine of theta and the cotangent of theta. There's a couple ways that we can knock this out. My suggestion, just if we're only evaluating unit circle. Now, if you don't have a complete unit circle right in front of you, where would you find it? The very front of your book. Now, over the next week or so, just so you guys know, in the very front of your book on that unit circle page, there's a lot of extra stuff. We are going to be looking at and dealing with almost literally, every identity out of here. So, these problems, if you have the unit circle, piece of cake. And let's see. Here's a unit circle that we can all use just to think about stuff. Only 2 steps. Can you find me 2 pi thirds? It's 2/3 of the way through a half circle, which is a weird way to think about it, but that's how it goes in my mind. It's here. If I'm asking for the sine of it, it's the what? The y value. Now, every time, and I'll throw that back up there, what is the y value or the sine of 2 pi thirds? A little louder? Root 3 over 2. Done. Okay, the cotangent is a little bit harder to think about. To find the cotangent, you need to make sure that you recognize our ideas. Now, we're not using the triangle yet. We're just using the unit circle as kind of a refresh. We'll draw a triangle here in just a moment. The cotangent. Now, with opposite adjacent and adjacent opposite, is it super duper easy to think of these things? I would argue no, because I don't see any triangles up here. However, nope, that's not what I meant to do. If we take this guy and throw it up here and use our wonderful bow ties and butterflies device or memory, whatever you want to call it, could I make it a triangle? From the origin to here, there's my 2 pi thirds, and this is the right triangle that we're thinking about. Now, from that idea, if I get rid of everything else, and not truly everything, I'm going to keep those values up there for just a second. I want to know what is the adjacent length to my angle theta, which is the angle right here that we're looking at. Kind of. We'll deal with that. That's the triangle angle, right? Cool. What's the adjacent length according to this point up here? Love it. And the opposite side length is root 3 over 2. And this one's not written here, but wager to guess what the hypotenuse is? It's 1. Could you Pythagorean theorem it out if you wanted to? Or you recognize it. Which circle am I using to do this? The unit circle, which means that is definition a radius of 1. Now from this angle, if we want to find the cotangent, I know it's the adjacent over the hypotenuse. From that angle, theta, that we have identified on this triangle, what's the adjacent leg? Negative 1/2 over, what's the hypotenuse? 1. What's the cotangent here? It is. What did I do? Hypotenuse. I was talking about cosine there, eh? Was it on purpose? No, not even a little bit. Opposite. Thank you, Fern. What's the opposite length? Confidently whispered root 3 over 2. Can we leave it like this? Not a chance. How do we deal with it? Okay, so that's negative 1/2 times 2 over root 3. Okay, we may do a little bit different stuff here. I imagine at this point we're probably pretty close. I'm going to automatically do that. I see it's negative 1 over root 3. Can we keep that? Not in here. Why? The radical. So we have to multiply by a clever choice of 1 real quick. Root 3 over root 3. And we end with this, and you might not have to show all this work, right? Maybe you do, maybe you don't. Either way is fine with me. What is the cotangent then of 2 pi thirds apparently? Negative root 3 over 3. Now, we could do it with the right triangle up on the board. It works fine. You can think about it. If you don't want to physically draw the right triangle, could you do all the same stuff just using unit circle? As long as you recognize that y over x or x over y for cotangent, and you have the values on the point, they're easy. If they're not these convenient angles, maybe it gets a little bit uglier. No different in the way that it works though. Okay, should we do another one like this, or you guys feel okay so far? Okay, no big feedback here. There is something awesome that we're gonna find, and we're just gonna reason it out. I'm gonna give you guys a moment, and we can call this, I'm gonna give us the name of it, the tilde, I suppose. Functions and their cofunctions. Now, this seems, when I first write this, it seems like really complex language. Sine is a function. I'm just going to tell you that. It's a function that you plug in an angle and it spits out a ratio. Fine and dandy. That's just a definition. Any guess on what the cofunction for sine is? Cosine. Absolutely. What's the cofunction of tangent? Cotangent. And the cofunction of secant? Cosecant. The language works really well there. There is a relationship. I'm going to ask that each group does a different angle, and we're going to compare what happens. Or we can just look at the unit circle, but we'll see it. For our first one, you do not have to write it down. I just don't want to lose track. Let's pick an angle theta to deal with. What's your favorite angle on the unit circle, JV? Why? Okay, it's a good one. Cool. 2 pi thirds. Here's what I want to do. First of all, to make this a little bit more easy, I'm going to regret asking you that. We're just going to use pi thirds. There's a reason for it, I promise. There's pi thirds. Okay, if I asked you for the complement of this, and that's, I am going to ask you, what is the complement? Right off the bat, chat with your neighbors. I'm not even going to pause the video. We have pi thirds. It lives in quadrant 1. I'm sure of that. I want to know what is its complement. I'm going to call this its complement. You want phi or beta? I'm going to call it phi for now. How'd you get pi 6? Okay, so you converted to degrees to think about it. That's completely fine with me. No issue there. What if I wanted to say never changes to degrees? Whatever phi is, I know that theta and phi better add up to what? If they're complements. Has to be pi halves. Okay, and we knew theta was pi thirds, right? So without ever changing to degrees, it's a little bit more cumbersome, but can we solve this? In fact, I want you to solve it. I'm expecting pi 6, but verify to me that your mathematics agrees with that. Yes, sir.
I mean, you said this, but why this?
So we're going to find, and that's a good question. We'll see why I'm having you guys do this here in a second.
Is this pi over 2 is given?
Yeah, so
Find this.
2 angles are complements if they add up to 90, right?
Right.
But instead of 90 degrees, we're just calling it pi halves radians. Yep.
Yeah.
So this is just the complement in radians. I'm leaving an awkward space for a reason. Everybody subtract pi thirds first. And then common denominator 6. So I'll go 3 over 3, and I'll go 2 over 2 to not really change anything other than the way it looks. And I'm pretty sure this is going to shake out the way we want it to. The complement of theta, or phi in this case, that's 3 pi 6 minus 2 pi 6. It is pi 6, 100%. So Sean, you're good to use the degrees. And actually, I probably would use degrees as well rather than doing this. But it's a good reminder to make sure that this clicks.
What's the multiplication?
What number am I allowed to multiply by? So I need a common denominator. And this is just my showing the work of when we make a common denominator, we just multiply by 1. Okay, so we now have that phi, or the complement, is pi 6. Everybody agrees with that? Okay. Here's what I want us to think about, and these are going to be the first of what we're going to refer to as our identities, which, random question, Riley, you used the word identity earlier. From where did that idea come? Like, do you know why you, I don't remember the question. Do you know why you answered identity earlier? Okay, I see what you're saying. If I wanted identity to be the answer to that question, just to clarify, I would, like you're thinking matrices maybe and multiplicative identities, I would ask something composed with its inverse produces what, and the answer would be the identity. But I'm not even a little bit concerned about that. Okay, I'm going to give you guys a second. I'm just erasing this so I have some work or some room to talk about this. What I want you guys to do for a minute, and you're going to make a generalization for me, but it's a simple follow-up question. How does and I'm going to use sine right now in this example. Sine of theta compare to the cofunction, which is, what's the cofunction of sine again? The cosine of phi. Okay, using your unit circle, you can use 30 and 60 or pi 6th and 2 pi thirds, but I want you to look at them. I want a nice, easy answer to this, and it's not going to feel obvious. The next step, once you get it, check with me, but same question, how does the sine, or give me another trig function that's not a cofunction. Tangent of theta, and I'm going to ask, how does it compare to what? The cotangent of, not theta this time, phi, if you didn't remember. Okay, there's one more version of this, the secant. We'll flop it around this time, of phi and the cosecant of theta. And now they're just swapped around. I'm going to give you guys some time. Play around. I'll check in with you guys as you're working through it. I want to know the relationship between the sine of an angle and the cofunction of its complement. See if there's anything nice that shakes out. We'll pause it here, and there will be a spoiler in 3, 2. The sine of phi, or theta, sorry, the sine of pi thirds. Sine of pi thirds is root 3 over 2. If you didn't write this, you're going to have a real hard time generalizing if you don't write stuff down. The first one maybe not, but the next one's for sure. What's the cosine of its complement, pi 6, Riley? Don't doubt, you got it. It's root 3 over 2. Something patterny showed up there. And we can do it with another angle here in a minute, but I'm fine with that for now. Tangents are a little bit harder. What is the tangent of pi thirds? And I'm going to do some scratch work over here. I don't care if you actually evaluate it on your own or simplify it, but I want to make sure it's there. Tangent is y over x or x over y? So the y of pi thirds, I think, is root 3 over 2. And the x then must be 1/2. And when we flop this, it's just root 3. Okay, I want you guys to do the same thing for the cotangent of pi 6. This time it's x over y, right? Huh. So that's root 3. And the cotangent of its complement, pi 6, was also root 3. If there wasn't a trend before, I imagine it's starting to show up now. What do you think is going to happen if we do secant and cosecant? And we'll just check it out without calculating. I want to see if we can generalize. The secant of phi, which is pi 6. So secant is the reciprocal of which function? Cosine. And I know that at pi 6, cosine is root 3 over 2. So this is 2 over root 3. Which we clean that up and it's 2 root 3 over 3. Okay. I'm just evaluating out using definitions that we have x over y, y over x, or whatever the case might be. Without actually calculating it. If I know that the secant of phi is 2 root 3 over 3, what do you think the cosecant of its complement theta is going to be? Louder. The same. It's the exact same thing. This is going to happen all over the unit circle with one little weird thing, because once you get past pi halves or 90 degrees, the idea of a complement kind of gets shaky. We will address that. There's a way to think about it. But seemingly, we have a relationship here that's going to be real nice to formalize. So, what we're going to get right off the bat are some identities. Immediately we get some identities. Now, in our sense, when we talk about identities, there's two different ways you can think about this. We all know the multiplicative identity. What number do you multiply by something to get the same number? So for example, 5 times what is still 5? That means that 1 is the multiplicative identity. I can multiply and it doesn't change. Okay, you can add stuff. Negative 2 plus what is still negative 2? Negative 2 plus 2. Okay. 0. My bad. It's still negative 2. That's an additive identity. When we talk about identities in the realm of trigonometry, what we're focusing on is equations that are true for every angle theta. They're always true. It's like saying 5 equals 5. That's an identity. It's a silly one, but it is an identity. Same idea, just looks kind of harder. But let's check it out, see if we can generalize. So, our first identity, and let's see where we're at here. We found the functions and cofunctions. We're going to give ourselves, and I want to make sure I use the same language as this book does, the cofunction identities. Cofunction. And it's trig, but I'm not going to put it because we're in the trig chapter. We get our cofunction identities. Weird, that word looks wrong when I write it in all caps. But it's not. I'm going to put a star next to this. We're going to have a bunch of identities in the coming days. Okay. Given an angle, let's call it theta. Given an angle theta, its complement, and before we called it phi, but I want to really think of what this means, can be found, or I'm just going to say is equal to, Not quite. Not quite. We're going to make this even easier. We're going to try just with degrees first because it's more natural. If I give you a 10-degree angle, what's its complement? 80. How did you get that? You're right. 90 minus 10, or 90 minus theta, right? So, we can have this two ways. If you want degrees, it can be equal to 90 degrees minus theta. That would guarantee a complement in degrees. Or what if I wanted that same thing in radians? Pi halves radians instead of 90 degrees minus theta. Before moving on, are you guys comfortable with just that idea? That's just a complement given. That's exactly how we found phi above. If you're not and you're just being quiet, I think I erased it all. But notice all the work that I had, we just did pi thirds plus something, is equal to pi halves, which if this is theta, we just subtracted theta from each side right off the bat. That's exactly what we had just done. So check it out. If you give me an angle theta, its complement is guaranteed to be this. Our co-function identities, there's 6 of them. I don't think I'm going to write all 6 of them. If I were to give you the sine of theta, I guarantee that is exactly equal to some function of 90 degrees minus theta. Now, the name here is probably going to just give it away, but these are the what identities? And what's the co-function of sine? Cosine. The sine of an angle is equal to the cosine of its complement every single time. And that symmetric idea that maybe doesn't feel like symmetry when you write it like that, but you probably noticed on the unit circle that the ordered pairs just flop places between 30 and 60. That is 100% this identity as you see it. Anywhere on the circle that you look. If you look at 2 pi thirds and 5 pi sixths, same thing happens. Cool. All right. What do you think is going to be true if I wanted to talk about the tangent of, and I'm going to switch this around. What if I wanted the tangent of theta of 90 minus theta? 90 degrees minus theta. What do you think that's going to be equal to? The cotangent of the complement, right? Which is just theta. Okay, the last one, let's get real wild with it. The secant of, I don't know, we're just going to pick a new angle. Just for, nope, I lied because we have this. What's the secant of theta equal to, guaranteed no matter what? You said cosine. I want to change that word. I think. Maybe I misheard. You said the right word, Huggins. Say it again. The... And I'm just going to change the format just a little bit. What if I wrote pi halves first instead? Is this still a complement if we do pi halves minus theta? Okay, double check your stuff. I'm kind of crazy sometimes. On every other one, do you have degree symbol? And if not, add it. Make sure you know you're talking in degrees if you're in degrees. Okay. Super duper hard. I'm going to let you guys decide here. We have 5 minutes left. I can give you the assignment for the first half of the section now. We can check it tomorrow just like normal. Or we can still talk just a little tiny bit more, and then it'll just be a single homework assignment that's shorter than the sum of the two that if I split it up. I can give you 4.3.1 and today and 4.3.2 tomorrow, or tomorrow I'll just give you 4.3 that's going to be those combined with some of the problems removed. Second option is a shorter overall, less overall work. Okay, so this is the first of our identities, co-function identities. Now, beyond this, we're going to start, and I don't have a ton of time, so that's fine, but we're going to start building up more identities. So let me see how your book names this. Cool. Some more identities. And a neat thing that happens here is we are going to have another section named exactly the same, some more identities, in a later, like probably 4.4 and 4.5. All right. So here we are, and I'm just looking. There's at least 8 sections in this chapter, so quiz is not after this section. First of all, we're going to add these, and we already have the co-functions listed. Okay, the only other ones that we're going to look at today, I think, are what we will call our reciprocal identities. Okay. We at this point in time have 2 ways to talk about the sine of an angle theta. I can say that it's y over r. That's the first way that we saw it. But I could just as easily say that sine is opposite over hypotenuse. And if you draw these triangles on any circle, what you'll find is that the opposite side length is y, and the hypotenuse is the radius. They're the same thing, just looked at differently. There was some noise out there. Everybody's still on track? Two versions of the definition. They're synonyms, essentially. Okay. As we look at this, I want you to look at your stuff that we did today. If I give you sine of theta is opposite over hypotenuse, cosecant is just what? And give me a word for what just happened. Opposite over hypotenuse changes to hypotenuse over opposite. Louder? The reciprocal is, yeah, it's a reciprocal. So check it out. There's some ways that we can do this. If I want to talk about the sine of theta, we can say it's y over r. I'm good with it. We can say it's opposite over hypotenuse. I'm good with it. This one feels less natural the first time that we write it, but it becomes so much more valuable. Sine is a reciprocal of what function based on just the way we always write it? Not cosine. Cosecant. Now, how do you find a reciprocal of something? Like, what's the reciprocal of 2? How did you get that? And put a what in the numerator? I guess even, yeah, just flip it if there's a 1 there already. So what did you guys tell me was the reciprocal of sine just a second ago? That means that 1 over the cosecant of theta. This is just another way to write the reciprocal. I just flipped it. This is a reciprocal identity. Sine is 1 over cosecant. Now, in contrast, how do you think we could write the cosecant of an angle using the reciprocal? Same idea. One over sine theta. Perfect. Okay, I kind of fibbed to you. I want you guys, these are listed in your sheets on the front of your page. Eventually, once we get through them all, this will become a handout for you guys, just so you know, which is what you would probably use on the chapter 4 test. This will be your cheat sheet. I will make copies. I'll print this out for you. We need to build them all, though. Without looking, I want you to try to do the same thing for the cosine of theta and the secant of theta. And one more time for the tangent of theta and the cotangent of theta. This is your not formal, but you should do this and you need to do this. This is your homework. Finish that in your notes. Cool.